Today we're going to shift from getting a simulation to run once to engineering it so the result survives a restart, a second or simply fresher set of eyes, and a later rerun. The idea is pretty simple. Make the code easy to inspect and test, but hard to fool. By the end, you should have a checklist. Keep notebooks tidy enough to rerun, move reusable logic into a small package, write functions with clear contracts, add small unit tests, practice debugger habits, and record enough run information to reproduce a result later. This simulation engineering workflow is a bit more complex than what you used for the first project, but it is reinforced in the worksheet. The more fundamental idea is used in the project. Start with the small model we understand, move repeated logic into functions, put those stable functions into modules, test known cases, and then use the notebook for experiments and, often, even for crusty folks like me, finding bugs to fix in the next round of revisions. The project layout is deliberately simple. The notebook tells the story, the source directory holds reusable code, tests have checks, and the driver gives the debugger something small and repeatable to run. Just about every project of mine uses a similar format, and we'll find in Project 3 that it's very easy to go from this layout to a deployable module that you and others can install and import. For sure, a tidy notebook is in part about aesthetics, but it's also about reducing what I'd call a hidden state. Restarting and running all cells often is a good way to make sure a result in cell 3 does not depend on a result in cell 10. Moving repeated calculations into functions helps to minimize this from happening too, and we get the benefit of having something we can test outside the notebook. The worksheet uses Jupyter Magic as a practical way to initialize the layout and create the module files right in the working directory. When I run this, I produce the sample source code that I need. I've done that all here in my NE415 folder. What this does is to turn all of the structure we laid out before into actual files and directories on your system. So for me, that's in my NE415 slides directory, and that has this src, or what I'll call the source directory. This additional magic, ls, lists out all of the contents of that source directory. I have the init.py that should be empty, and the other files that I expect to have been created. A useful simulation function has one job and a visible contract. Before I trust it, I want to know the inputs, the return values, the units or shapes, the local validation done, whether prints or plots as a side effect. Printing and plotting belong at the notebook or reporting layer, not hidden inside some low-level helper function. If you do that, you're going to be, well, annoyed with yourself at best. What this cell does is to write out the statistical functions that we'll use for this demonstration module. The examples are intentionally simple and easy to check by hand, and we can use them to model the habits that we want to use for more complex simulation functions. A docstring documents the function contract. It should answer the questions a caller has before reading the implementation. What the function computes, what the inputs mean, what units or shapes are expected, what comes back, what can fail. This is the same idea written out. The docstring records that x can be array-like, that low and high are bounds in the same units as x, that the return value is an array, and that low greater than high raises a value error. In a simulation, small ambiguities like inclusive bounds or unit assumptions can change the interpretation of a result. Docstrings are also useful while you're working, because writing the contract forces you to decide what the function is supposed to do before you ask ChatGPT to finish it. Kidding, of course. The help call shows what another user sees from the notebook, a terminal or an editor. If this output is vague, the contract is vague. That usually means we haven't organized our thoughts enough, so a bit more time planning a solution would help a lot. Here, I think this function clamp is pretty well documented. And when behavior changes, the tests and the docstring should change together. The test protects the behavior, and the docstring explains the contract. So if they disagree, one of them is, I suppose, lying. Now that we've got our Python source file, I can open it in VS Code, edit the docstring, save it, and come back to the notebook. I can open up the debug driver, and see that it's exactly what I printed out from the notebook. Once the logic lives in the Python file, the notebook can import it like any other module. This is how we use the notebook to drive examples, plots, and discussion, while the reusable logic lives in source files. That makes the notebook almost like a user interface for our own code. Great, now the notebook calls the functions directly from the module file we wrote. Executing them, we see that the outputs are intentionally very simple, and we get our mean and standard deviations that we expect, and we see how clamping drops at 99 to a 10. Unit tests are small checks with known answers. They don't prove that a whole simulation is correct, but they help us catch small errors before those errors hide inside a long run. A good test answers one really focused question. This test writes a representative unit test file. It imports the unit test module, defines the teststats class, and asks small questions, like does the mean give the obvious average? Does it raise on empty data? Do we compute the right sample standard deviation and clamped array? When I make unit tests, I almost always start from a previous example that looks like this to avoid all the boilerplate stuff like the imports and having to look up common assertion names and so on. All test functions have to start with test. And usually, I'll put test underscore. I reiterate, each test answer should answer one small question, and it's a pretty good idea to name the test something clearly indicating what that question is. Tests can be run from the terminal or from within the notebook, but inside a notebook, the discovery workflow can be run directly. We import the unit tests, we look for the tests using the test loader and discover function, we build the runner and then run the suite of tests, and then we see what happens. In our case, all 4 tests passed. Defensive programming means we try to fail as close to the cause as we can, and that's often with the user. If we check that positive inputs are actually positive, or that an array has the right number of elements before we use them, we can save ourselves a heck of a lot of wasted time later on. This function shows the idea in action. It converts inputs to a numeric array, rejects negative probabilities, checks that the total is positive and finite, and then returns normalized values. Now, we might not always be so picky when writing functions we expect to use for one homework and then toss, but it's not a bad idea to be defensive where you can. In the lesson worksheet, you'll be given a debugger target file. That function, first crossing, is small enough to reason about by hand, but it still has the loop and branch structure that makes debugger practice pretty useful. We also have a genuine contract question. Does crossing mean greater than, or equal to? This writes out that same crossing function. The function converts the input to an array, handles that empty case, and then returns the first index whose value is strictly greater than the threshold. The word strictly matters. If a value equals the threshold, this implementation does not count it as a crossing. This driver script gives the debugger a tiny reproducible case. It imports our function, sets x in the threshold, and prints the result. To use the debugger, I have to set a breakpoint, and I want to take a walk through the execution of first crossing. So here's what I'll do. I'll single click there to add the breakpoint. I noticed here that I didn't select the interpreter. It seems like that should be okay. Yeah, that's just fine. Okay, so I've set this breakpoint. Now, what I want to do is figure out what's happening to variables as I call first crossing and it does its thing. So the first thing that I can do is go over here to the runner debug. It starts off as this play button, hit that down arrow, and then Python debugger, debug Python file. There are a couple ways that we can get to this, but this is one option. Of course, I get this exception because the NE415 tools module isn't there. It's not in my path. What do? The easiest thing that I can do, and shame on me because it's probably not the proper thing to do, is simply append to the system path from within the file. The way I do that is as follows. Import sys, and then sys.path.append, and we will do ./ means our current working directory, and then src. That means that it will look for our module named NE415 tools, in the SRC folder, and it does exist there, and we have these Python files. So I'll save it and run it in debug mode one more time. This time, it worked. In order to enter first crossing to see what's going on, I need to find the right next step. In our case, that's going to be step into. We all have these options. Most debuggers in these sorts of systems seem to work about the same. These are the same features that I've seen in, say, Spider, another tool that you might have seen in the past, Eclipse, the Visual Studio stuff. You have these things: continue, step over, step into, step out of, the restart, and then, of course, stop, which just terminates the debug session. So we want to do step into, because that will mean go inside of this thing with the parentheses, the thing that we're actually calling. And so here we are in the crossing.py module inside the function definition first crossing. And we're at this line, x is equal to this array. We haven't actually executed it yet. That's going to be the thing that happens. But because of our calling function, we were given that x is equal to the array. So that because we're in debug mode, we know what was given to first crossing. So it kind of fills that in for us. That means that we have local variables. And one of them is the threshold. That's the 0.49 that we called first crossing with. That's this thing here. And then we just talked about the x. So looking at this, of course, the size is not going to be equal to 0, so we're not returning a -1, and then we go through. Because the threshold is 0.49, we know that the 0.5 is the right answer. So we can step over this as array. We can step over this if, because it won't be evaluated. We can step into this for and keep doing the step into and look at the values of I as I change. We are now at I is 1. We have the x value 0.2 that will be compared, so on and so forth. We're at 2. That is a value I equal 2. That is our 0.5. That actually is bigger than this threshold, so we should get to the return -1. And we did, and it sent us back out. And we get our index, which should be the 2 that we found. Step one more time. We have the print, the threshold, the first crossing. Easy peasy, lemon squeezy. Import confusion is common when notebooks and modules interact. The notebook may have SRC on its path, while the terminal does not. A saved file may differ from a function already loaded in memory. Be careful with paths and remember to restart the kernel when you make changes. Printing these two files gives us a very quick way to see what files Python is actually using. It's a quick check. If the path on the screen is not the file you think you edited, you've found a problem. Reproducible random numbers should be initialized at the top level of your simulation script, perhaps in a main simulation function. A low-level physics or sampling function should receive the generator or receive already sampled data, whichever makes sense, rather than hiding a seed internally. The seed is part of the run information, so we don't want it to change along the way. I've done that, and it's a terrible bug to find. With a recorded seed, we can recreate the same sequence. That means if a particular random history exposes a bug, we can come back to the same case instead of hoping it appears again. Flowcharts make branching logic visible. A simulation history usually has many repeated steps, like sampling the distance, checking a boundary crossing, and so on. If the flowchart is confusing, the code probably is too. Just be thankful you live in an era without goto statements. The classical Jupyter notebook that I use here doesn't actually render the mermaid diagram. Because of that, I've actually opened up the notebook here in VS Code to show you that diagram as you should probably see it when you create these diagrams in Jupyter. A repeatable simulation run records model parameters in units, the random seed, the number of histories, the generated figures, and the data behind those figures, and which tests passed. The goal is that someone else, including the future you, can rerun the case and understand what changed. Lesson 10 uses the same engineering instinct for deterministic balance laws. We'll name the unknowns, write the equations, solve the resulting system, and then verify the solution. The tools will change, but the habit is the same. We've got to make the model explicit, we've got to compute carefully, and we always got to check what the answer means.